So the application, there's a lot of exhaust byproduct from an internal combustion engine that is just wasted to the environment. So it's a lot of heat that could be used to power other systems such as a car's alternator. If we can use the heat from an exhaust system to cover the alternator, it'll increase the vehicle's fuel efficiency. And it's real simple. A thermoelectric generator just takes a difference of heat and it outputs a voltage. So the higher the difference we can get, the more voltage we'll produce. The problem that a lot of companies have ran into when developing products like this is the viability of producing a large volume and commercially viable product. Okay, this is our proposed concept. We just chose a baseline thermoelectric generator device. It's the TEG Pro high temperature 5-watt module. It can withstand higher temperatures than 300 degrees C because we understand that an exhaust system is above this, but the highest temperature that it's going to register is a hot side temp of 300 degrees C. So we went off of this for our calculations. The cold side temp is 30 degrees estimate, and we did this because the implementation of a secondary heat exchanger to cool the thermoelectric generator with the engine's coolant will get the temperature down to this level. And it's really important to do that because, as you can see in this image, the colder that you can get the cold side thermoelectric generator, the more output power you're going to get. So after we calculated that, we determined that we can generate 5.2 watts of energy. We chose a baseline alternator. It's a 12 volt 70 amps generator, which is about 840 watts, and we found this from AutoZone. So using that, we determined that we need a total of 162 thermoelectric generator modules working in series to get enough energy to power our alternator. All right, so here's some background on some existing technology that's already out there. The top image here is a US military funded and developed product. It's a 1 kilowatt thermoelectric generator that they used in their Bradley fighting vehicle. And it was particularly attractive to the military because it was highly reliable and had very low maintenance. And as you can see, it's kind of cool because they split the exhaust so that you have more contact between surface areas of the thermoelectric generators. Another study that was done was by General Motors. They did a thermoelectric generator design and prototype build, which helped improve fuel economy with their Gen 2 Scutterdike modules. It was a modular design that improved performance flexibility, it gave them efficient packaging and adaptation to a wide variety of vehicle platforms. So this was important because GM has a number of different vehicles out there. They wanted something that is easily compatible with every single model. And this is an image of that model here. As you can see, they kind of followed the same design where they split the exhaust, but it was also flexible. So a cool thing is that they were able to wrap the exhaust system with these to once again give them more surface area contact with the hot side. So these are some of the calculations that we started to do. Based on a lot of research we did, specifically on the US government site, we determined that by reducing the electrical load on a car's alternator, you'll increase your fuel efficiency by about 8%. Some of the assumptions we made for the calculations, we determined that we'll use a 15 mile per gallon baseline. We decided that 12,500 miles driven per year is the national average, but we also tried to stay conservative on a lot of our assumptions. So if you drive more than that, you're going to decrease the simple payback time and get your money back a lot quicker. And we also assume that $3 per gallon is a good assumption. The first calculation we did is to determine the number of gallons that you'll save per year. So to do that, you just divide the number of miles that you drive per year by the miles per gallon and then multiply it by the percent improvement that we determined up above. So we calculated that you'll save 66.67 gallons per year, and then multiplying that by the price of a gallon of gas over the past 10 and future 10 years, we determined that you'll save approximately $200 per year. The image is important because it shows the percent of global greenhouse gas emissions by each economic sector. And we're in the transportation sector, so 14% of global greenhouse gases are produced by cars and vehicles driving on our roads. Alright, so this slide is just going to explain how we calculate our simple payback. The installment costs are listed here. 162 thermoelectric devices cost about $2,400. Adding a second radiator system to cool the coolant is $31. We assume that this process will take about an hour to install. So we made the assumption that that's $100 per hour. Housing fabrication is about $200, so the total installment comes to $2,792. That installment cost divided by the annual savings, which was $200, will give you a simple payback of approximately 14 years. In summary, our idea is pretty simple. We want to take waste heat from a car's exhaust system and use it to power a thermoelectric device. To increase our delta T, we're going to take coolant from the radiator, and by increasing our delta T, it's going to create the largest voltage output. With that voltage output, we want to completely reduce the alternator from the vehicle, increasing the fuel efficiency by about 8%. So we want to do further testing to determine how to decrease the simple payback period. So from our analysis, it has been determined that this idea does not save money until the lifetime of the vehicle is complete. But we also feel like it's really valuable because it does a lot by decreasing fuel efficiency and saving the environment. If you can remember earlier, about 14% of the greenhouse gas emissions comes from transportation. So by decreasing fuel efficiency through every vehicle by 8%, we can do a lot to save the environment.